Now we want to think a little bit about polynomials of the form linear times linear times linear times linear. Now, if you have a bunch of linear factors, two of them could be the same. So you could share a zero. Now, we've already seen what you do with that, but we're not going to consider that possibility right now. We're going to consider only a function with distinct zeros. So here we have one, and here I've indicated the zeros. I put a little x on each point to indicate we've got to go through all these points. Okay, now we can analyze the positives and the negatives. Now on this side of -6, everything's going to be positive. Sorry, everything's going to be negative. But that's going to make it positive since you got 4 negatives. Between -6 and -4, what are you going to have? You're going to have 3 negatives and a positive, which gives you a negative. If I pay attention to what I'm doing, might not make that slip up. Okay? Between -4 and 3, and you can verify this yourself, you're going to have 2 negatives and 2 positives. Not necessarily in that order, but that's going to give you a positive. So the polynomial is going to be positive here. Here you're going to have 3 positives and a negative, which makes it negative. And here you're going to have all positives, which makes it positive. The overall shape is that of an x to the 4th graph, which is a lot like a parabola, but it's a little flatter on the bottom. So your basic shape is that of an x to the 4th, which means it's going to be very high. It's going to approach this 0 here from a very large positive value, and after you hit the 5, it's going to go up toward a very large positive value here. So the graph is going to probably look something like this. Okay, it's going to come down here through the positives. It's going to go negative here. And then it's going to come back up through some positives and probably get pretty big here. And then at some point it'll turn around, so you can come down here, go through this point, and then go up. Okay. Now we notice that this graph has 1, 2, 3 turning points. The degree of the polynomial is 4. The degree is the power of the largest exponent that you have on one of your x terms. And since we have 4 factors here, we're going to have an x to the 4th. So this equals x to the 4th plus a bunch of other stuff. Okay? And let's see, what are we going to have? We're going to have a -8 and have a 4x cubed and a bunch of other stuff. That's not going to be a 4x cubed, it's going to be a 2x cubed. Anyhow, you can multiply it out, you can use the distributive law, but the point is, it has a degree 4. So, and as we've seen, the highest degree term tells you what the graph is going to look like if you go far away from the zeros, and you don't have to go all that far away. It's going to act like an x to the 4th graph with a couple of little wiggles in here. Now the wiggles come about because it has to go through the x-axis at the zeros. There are 4 zeros, so it's got to turn. It can go through this 0, but it's got to turn around before it can go through this one. So there's one turning point, and then it's got to come back down to here, so it's going to need another turning point, and now another turning point down here. Now this at least makes plausible the rule maximum possible number of zeros, or number of turning points is one less than the number of the linear factors. I started to say one less than the number of zeros, because that would apply here, but I could change this polynomial by raising it up above the x-axis just by adding a number onto the end of it, and the expanded form would still be a polynomial, but it would be up higher and it wouldn't have any zeros. But it would still have the same turning points because just adding a number of this just vertically shifts it. Okay, so I just said something that doesn't make any sense at all. This has the linear factors, it has the zeros. So I have to change that. Change my mind. One less than the degree of the polynomial. Okay. Again, the degree I'm not sure I want to try to make this argument because it's a little bit abstract. I'll say it anyhow in case anybody, but you can stop here if you want. There's your rule. Okay? By vertically shifting this, we don't change the number of wiggles. Okay? So we can get this many wiggles for a degree 4 polynomial. We can't get any more than that because if we have more than 3 wiggles, then if we raise or lower it sufficiently, we're going to have at least 5 zeros. We're going to have too many zeros. Okay, so I don't want to get into the rigor of that argument, but since I mentioned it, there it is. Okay, now the lessons again. Got a polynomial with 4 distinct linear factors. The graph can have as many as 3 turning points. With a little more argument, you can come up with this rule. The maximum number of turning points is 1 less than the degree of the polynomial. It doesn't have to be equal to the degree of the polynomial. For example, this polynomial has degree 3, but it has no turning points. Or maybe it has no turning points. It doesn't have to have turning points. So I'm not going to say any more about that because it gets a little beyond the scope of the course. In a calculus course, you learn to do more analysis about inflection points and higher derivatives and so forth. Okay, so there we have it. Now for problems, I might well ask you, well, what if we had 5 distinct linear factors? Okay, what could it look like? If we had 5 distinct linear factors, we'd have 4 zeros, which means we might need did I say that right? At 5 distinct linear factors, we could have 5 zeros, which means we could have as many as 4 turning points. Okay? Whatever your number of linear factors is, you can have that many turning points.